Hello everyone, welcome to EEEE lecture number 8. Uh, we will solve first a numerical on Thevenin's theorem using Thevenin's theorem. So let us do that. So in this numerical we need to find current through 40 ohm resistance using Thevenin's theorem. So I'll mark my 40 ohm resistance. So this is my value of RL. This is my load resistance RL. And I'll mark the points over here as A and this will be point B. Now let us solve this further. So for the first part, we will calculate RTH, that is Thevenin's resistance. So we'll write the solution. So first we'll find or calculate RTH. So what is the procedure to calculate RTH? So let us write it down point wise. So first we need to remove RL and then um, over here we need to replace the voltage source with its internal resistance. So replace 2 volt with its short circuit. So replace 2 volt voltage source with a short circuit. That means we have to short 2 volts voltage source. Alright. So remove RL and replace 2 volts voltage source with a short circuit. So let us draw the circuit for calculating VTH. Let me minimize it. Alright. So let me take this color as blue. So I am drawing it over here. So over here we have 10 ohm resistance. This will be 30 ohm. Now when I sort this 2 volt voltage source, we will have over here. So we'll sort this terminal and this terminal. Let us mark this point as C. Okay, over here. So these two terminals are getting sorted. So this point is C. This is point A. This will be 20 ohm. This is 15 ohm. And this is point B. Alright, so this is my equivalent circuit by removing RL and by short circuiting 2 volts voltage source. Alright, now we have to solve this further. So if you see carefully, this if I draw it in a more conventional manner, I'll get this 10 ohm and 30 ohm will be in parallel. So this is 10 ohm, 30 ohm will be in parallel and then it is connected to point C. This is point A, terminal A, and then again 20 ohm and 15 ohm are in parallel. Here it is, and this is B. So this is 20 ohm and 15 ohm. So basically over here we have 10 ohm parallel to 30 ohm, that will be around 7.5 ohms, and here we have 20 ohm parallel to 15 ohm, that will be 8.57 ohms. Alright, let me redraw the circuit now. So here we have A, then we have 7.5 ohms, then we have C, and then we have 8.57 ohms resistance. This is B, this is A. So what will be RAB? RAB will be the series combination of these two resistances. So what do we write over here is RAB, which is equal to RTH, is 7.5 plus 8.57 ohms, and that will come out to be 16.07 ohms. So that is the value of Thevenin's resistance. Alright. So next we will measure VTH. We'll calculate VTH. So let us write it down. Second point. Second point is measure open circuit voltage VTH. VTH or VAB or VOC. Alright. So what is the procedure? The first point is remove RL. Remove the load RL. And the second point is then we measure open circuit voltage between A and B. Okay, this is VAB or open circuit voltage or VTH. Alright, so we have to draw the same circuit, okay, without connecting the load RL. Alright, so if we don't connect the load RL, then this 2 volt I can show it between these 2 points directly. So let me draw the circuit again over here. So here we have 2 resistors, another 2 resistors over here. So instead of showing it from outside 2 volt supply, we can show it from inside like this. Alright, and these are my points A and B, and this is connected to the ground. Alright, that is how it is. Yeah. Okay. So now this will be 10 ohm, this will be 30 ohm, this will be 20 ohm, and this will be 15 ohms resistance. Now we need to calculate VAB. So we can simply apply mesh analysis and find using that. Even simpler technique is by using Ohm's law. Now if you see carefully in this network, we have two resistances and one voltage source. This voltage source value is 2 volt. Alright, so the current I1 flowing in the network like this. I1 is flowing in this network. So what will be I1 given by? I1 will be 2 volt divided by 10 plus 30. So 2 volt divided by 10 plus 30. That will be 2 by 40 amperes. Similarly, here we'll have I2. So I2 will be like this. So I2 will be 2 volt divided by 20 plus 50. 20 plus 15. So it will be 2 divided by 35 amperes. Now that we got the value of I1 and I2, we need to calculate VAB. So for VAB, we need to start with B and then go to A like this. So direction of flow is from bottom to top. So when you go from bottom to top, what is VAB? So VAB will be equal to, now when you are going in this flow and the current direction are the same, so we will get minus 15 I2. Over here we have the current direction as opposite and the flow is opposite, so you'll have plus 30 I1. Alright, so we'll calculate the value of VAB now. So VAB will be minus 15 into I2, which is 2 by 35, plus 30 into I1, which is 2 by 40. So if you work it out further in calculator, you will get VAB equal to VTH, and that is coming out to be 0.64 volt. Okay, so that is my value of VAB. Now we can draw the Thevenin's equivalent circuit and find the answer. So here we have less space, so let's draw the Thevenin's equivalent circuit over here. So we'll solve the part C part over here. So we have to draw Thevenin's equivalent circuit. Okay, so what is Thevenin's equivalent circuit? VTH, then we have RTH, then we have point A and B, and then we connect back your RL. Alright, so if we want to find the current flowing through 40 ohm resistance, so we have to connect this as 40 ohm. This will be 16.07 ohms, and VTH is 0.64. So if we need to calculate the current flowing through 40 ohm, so I 40 ohm will be 0.64 divided by 16.07 plus 40. So I of 40 ohm will be, if you work out in the calculator, this will be 0.011 ampere. Alright, so this is the value of the the current flowing through 40 ohm resistance, and direction is going downward. So this is the answer by Thevenin's theorem. So the current flowing through 40 ohm resistance will be 0.011 ampere. Alright, so we have completed this numerical and we got the answer of current through 40 ohm resistance will be 0.011 amperes. Alright, now we have completed 3 numericals, including the last 2 lectures. Last lecture 2 numericals we have solved. So we have solved 3 numericals on Thevenin's theorem, and now it's the right time to start with Norton's theorem. Okay, so in many ways Norton's theorem is quite similar to Thevenin's theorem. So what happens is, let's say you have a complex circuit. Okay, so this is my complex network or my complex circuit consisting of voltage sources, current sources, and various resistors, and we have output terminals connected between A and B, and we have a load resistor connected to it as RL. Now this, according to Norton's theorem, will get converted into a current source in parallel with a resistance Rn. Okay, so this is called as Norton's current and Norton's resistance. This is between point A and B, and between A and B we'll connect back here RL. So this complex network got converted into a single volt current source in parallel with a resistance Rn. Alright. So this is your Norton's equivalent circuit. So this is Norton's equivalent circuit. Alright. So in Norton's theorem, we have a current source which is in parallel with a Norton's resistance Rn. So In and Rn. Alright. So we need to calculate the value of Norton's current. It is also called as a short circuit current. So what do we do over here is we remove load RL and we short circuit the load terminals A and B, and we measure the short circuit current between the points A and B. Alright. It is called as IN or short circuit current. Then for the calculation of Rn, Norton's resistance, the procedure is same as RTH. That is, we need to remove the load and we need to deactivate the sources. That means replace them by the internal resistance and measure the value of resistance between the terminals A and B. All right. So this is what is Norton's theorem is. So Norton's theorem statement says that any two-terminal network, however complex, can be replaced by a single current source IN in parallel with a single resistance Rn. Alright, so that is Norton's theorem. Now let's solve a numerical on Norton's theorem. So over here we have to find the current flowing through 4 ohm resistance. So this 4 ohm resistance is my RL. Let me add over here. This is RL and these are my points A and B. Alright. Now we need to find first case. Let's start writing the solution. So the first case we need to measure Norton's resistance Rn. So Norton's resistance is Rn. So what's the procedure to calculate Norton's resistance? We need to remove RL. Alright. And secondly, we need to deactivate all the sources. So we need to deactivate all sources. That means replace the current sources with open circuit and replace the current voltage source with a short circuit. Alright. So let's do that. Let me keep this circuit over here and let's replace the current source with a open circuit. Then we have this resistor 2 ohm. Then voltage source will be replaced by a short circuit. Current source with open circuit. And then we need to remove the value of RL. So this is A, this is B, and we removed RL. And we need to find over here RAB or RTH. So if you see carefully, RAB or RN is nothing but 2 ohm resistance. Alright, so let me write over here RAB is equal to RN is equal to 2 ohms. I hope you are following. So the procedure is same for calculating of Norton's resistance. Alright. Now next we will find the Norton's current or ISC. Alright, so let's do that. So for the second case, we'll measure IN Norton's current or short circuit current. Alright, so now here also the procedure is remove RL and the second is short A and B terminals. Short A and B terminals and measure short circuit current, which is same as your Norton's current. Alright. So we have to keep all the sources intact and sort the terminals, remove RL and sort the terminals A and B in order to calculate the value of IN or ISC. Alright. So let's do that. Let me redraw the circuit over here. So this will be 5 ohm, 5 ampere current source. Then there is value of resistance of 2 ohms. This is 6 volt voltage source. Then we have a 2 ampere current source. And here we have a load A and B. A and B terminals, you have to short circuit it, means connected like this. So this is my IN or ISC. So that is what we need to calculate. Alright. Now, if you see carefully, we can simply apply a simple mesh analysis to calculate this. Alright. So now we need to calculate ISC. So if we apply normal mesh analysis, what do we get over here is, this is loop number 1, this is I1, this is I2 and this is I3. Now with a simple observation we can see that I1 is directly equal to 5 amperes. Okay, and mesh number 2 and 3 form a super mesh. Alright, because a current source 2 ampere is set between mesh 2 and 3. So mesh number 2 and 3 form a super mesh. Alright, so now we have to apply KVL across the super mesh. So this is the KVL, this is the super mesh what we have. So now let's apply the, let's write down the current equations relating the, because 2 ampere source is common between mesh 2 and mesh 1. So we'll get that equation, that will be I3 minus I2 is equal to 2 ampere. Alright, let's call this equation number 1. Okay, again I1 is already given as 5 amperes, it is 5 amperes. And now why I3 minus I2? Because I3 is in the same direction of 2 ampere current source. So we have I3 minus I2 is equal to 2 amperes. And now we apply the KVL to the super mesh. So we apply KVL to super mesh. The yellow color loop we have to follow. So over here we have minus 2 I2 minus I1. Then we are going from here positive to negative, so it will be minus 6, and here we don't have anything, so that will be equal to 0. So we get over here 2 I1 minus 2 I2 is equal to minus 6, is equal to 6 in fact. Then I1 is given as 5, so this will be 10 minus 2 I2 is equal to 6. So minus 2 I2 is equal to minus 4. So finally we get the value of I2 as 2 amperes. So this is my value of my current I2. Now I required a value of I3. So we have the relation that I3 minus I2 is equal to 2 amperes, and I2 is actually equal to 2 amperes. So what will be the value of I3? I3 will be around 4 amperes. Alright. So this I3 is same as IN or ISC. So let us write it down. This is my Norton's current or my short circuit current. So this is how we calculate the Norton's current. Alright. Now after doing this, we have to draw the Norton's equivalent circuit. So part number C is Norton's equivalent circuit. So let's draw Norton's equivalent circuit. How it will be? There will be a single current source in parallel. This is IN in parallel with Norton's resistance RN. It's connected between terminals A and B, and we connect back the resistor RL. What are their values? Well, the value of IN is 4 amperes. RN value is coming out to be 2 ohms, and the load resistor is 4 ohms. Alright, and we want the current flowing through RL. So by current division rule, I of 4 ohms is equal to other resistance, that will be 2 ohm divided by 2 plus 4 into 4. Alright, so current flowing through 4 ohm resistance will be coming out to be 4 by 3 amperes. Okay, so current flowing through 4 ohm resistance will be 4 by 3 amperes. Alright, so this is obtained using Norton's theorem. Using Norton's theorem. Now let's verify this quickly in LTspice. So let me open the LTspice window. Yeah, it is already opened. And let me implement the circuit. So first of all, we have to measure Thevenin's resistance or Norton's resistance in fact. So for Norton's resistance is very clear, it is directly equal to 2 ohms, so no need to do that. We will calculate ISC. So for ISC, this is the circuit. Let me make the circuit over here. So first of all, we have a current source. Direction is opposite, so press Ctrl R to change the direction. Then we have one voltage source over here. It is connected in this manner. Let me select it again. Okay, so connected it over here. Then we have a resistor of 2 ohms. Then we connect the circuit quickly with a wire. Let's connect the remaining part of the circuit. This will be 2 ohm resistance. Also don't forget to add the ground. So we'll add the ground node over here and connect it with a wire. So this value will be 2 ohms. This current source is 5 ampere. This voltage source is 6 ampere. And this current source is 2 ampere. Now these are my terminals A and B. So let me take it out. This is terminal number A and terminal number B. And they are sorted together. Okay, so no need to write terminal number A or B. They are already sorted together. Alright. So let's calculate the value of I3 from this circuit. So let me simulate. Click on run. Click on DC operating point and then click on OK. Alright. So over here the current flowing through the loop. Okay, fine, understood. So basically we need to find the current through this wire. So to find the current through this wire, we need to add an ammeter. Now there is no ammeter in LTspice. So we'll add a voltmeter which acts as an ammeter. So if we apply 0 volt over here, no harm will be done to the circuitry. In fact, all the functionality will remain the same. But the current flowing through this V2 will give me the Norton's current directly or a short circuit current. So let me simulate. Okay, so the current flowing through V2 is 4 amperes. As you can see, the current flowing through V2 is 4 amperes, and that is what your ISC or Norton's current is. Alright, and we can easily make the Norton's equivalent circuit and easily find the value of current flowing through 4 ohm will be 4 by 3 amperes. Alright, so that is what we have over here. Now let's get back to the handout. I hope it is clear. So in this manner, we can solve any numerical using your, you know, Thevenin's theorem, using Norton's theorem very easily. All right. Now let us continue with the further part. Okay. So now there is one more numerical given over here. All right. We need to find the current flowing through 5 ohm resistance using Norton's theorem. All right. So this is the circuit given to you. So what we will do is we'll discuss the strategy around it and we'll see whether we can solve this very easily. All right. So what is the current flowing through 5 ohm resistance? So basically your 5 ohm resistance is over here. So this is my RL. All right. This is my RL. So let me write over here, this is RL and these are points A and B. Okay, this is point number A and B. Okay, so now we need to find the Norton's resistance and then we need to find the Norton's current. Okay, so let's start doing it. So what we will do is we'll write the solution. Let me keep it over here. Okay, just wait a second. Okay, so for this numerical, let's sort it out and find the value of RAB. All right, or Rn. So let's do that. So solution, we need to calculate, find Rn, Norton's resistance. So for Norton's resistance, what do? We first remove RL and then we deactivate all sources. Deactivate all sources. All right. So we have deactivated all the sources. So what do we get over here is, let me redraw the circuit over here. So we have this current source as open circuit. Then we have this resistance. These are points A and B in which we need to find the equivalent resistance. This will be 6 ohm, 3 ohm, 10 volt voltage source will be short circuited. Then we have 2 ohm resistance. Then we have 10 ohm. This will be 6 ohm. This is open circuited. and here are the remaining resistances. So this is 3 ohm, 4 ohm, 6 ohm, and this will be 2 ohm. All right. So this is the circuit, and we need to calculate the equivalent resistance between terminals A and B. So if you look carefully, these three resistances are connected in series. So let's connect them, all of them together. So this will be 6 plus 9 plus you know 6 plus 4 plus 3, that will be 13 ohms. Now this 13 ohms and this 10 ohms are connected in parallel, but let's do it in the next step. So here we have 3 ohms, it is open circuited actually, and here we have point A and point B, it is open, right? Here we have 6 ohms, then we have 10 ohms, and here we have in parallel we have this as 13 ohms. Okay, so what will be RAB? This 3 ohms will become redundant because it is open circuited. So RAB will be, these two resistance next will be in parallel. Okay, so we can write over here 10 ohm parallel to 13 ohm. That will come out to be 5.65 ohms. All right. So now we are left out with, okay, we have one more 2 ohm resistance also connected over here. Sorry, this is 2 ohm resistance. Okay, so we have a 2 ohm resistance also connected over here. So now the circuit gets reduces to, so we have terminal A, terminal B, this is 6 ohms, then we have 5.65 ohms, and then we have this as 2 ohms. All right, so if you see carefully, all the resistors are connected in series. So equivalent resistance between A and B, or Rn, is 6 plus 2 plus 5.65. So that is coming out to be 13.65 ohms. So that is my value of RAB. All right. Now for the measurement of you know uh, IN, we need to calculate short circuit current. I have already done that in a numerical. So let me show it to you. This is that numerical. I'll show the value of how to measure the value of okay, this is Thevenin's theorem. Let me see if I have done Norton's theorem. Numerical number 8. Okay, we have calculated till this. Let me check if I have the answers for that in lecture number 9. No, not this. Okay, so we'll solve this further, and we'll calculate the value. Okay, let us check it out in parallel. Let me keep this over here. I've already solved it. I didn't have the answers. That's why I'm keeping this document as a reference. Okay, so now don't concentrate on the left hand side. Don't concentrate on the right hand side part. That is just for to check the answers. Let me keep it like this. All right. So now for finding the value of short circuit current, we need to sort the terminals A and B, and we need to measure the short circuit current. All right. And also I may draw the circuit again. So let me do it again. Okay. Now before drawing it again, I will do one more thing. Can I convert this a single resistance with parallel with a current source with as follows? It will be 6 ohms and a source transformation I did 12 volt. Why 12 volt? Because 6 into 2 amperes. All right. So I replaced this resistance in parallel with a current source with a resistance in series with a voltage source. All right. So let me redraw the circuit over here for measurement of IN. Okay. So let me write over here. Second case, measure IN. short circuit current. Okay, so to do that, what do? These are the two steps we follow. We remove RL, we short A and B terminals, and we measure short circuit current ISC or IN. So let me draw the circuit over here in front of you. So you can refer it your numerical. So we have 6 ampere current source over here. Then we have 3 ohm resistance. This is A and B. So between point A and B, we have to connect a short circuit. So this is the short circuit. Then we have 6 ohms resistance connected over here. All right. Then we have this 10 volt 2 ohm resistance. We have 10 ohm resistance. Now remember this over here, this 6 ohms will be replaced by 6 ohms and 12 volt voltage source. So let us do that. The 6 volts will be replaced by 6 ohms and 12 volt voltage source. All right, and then we have 3 ohms resistance and then 4 ohm resistance. All right, so it's simply a matter of applying simple KVL, and we'll find the value of the current. Mesh analysis simply. So this is loop number 1. This is I1. I'm denoting the current I1 in this direction, I2, and this is I3. So yeah, let's start. So if you look carefully over here, current I1 is basically directly 6 amperes. Even though there is a 3 ohm resistance connected, if it is in series with the current source, it will be I1 will be directly 6 amperes. All right. Now this is IN actually. Let me mark it. I haven't marked it. This is IN, which we need to find out. And what is IN actually given by? IN will be given by I1 minus I2. So we need to know the value of I1 and I2. Now let's go to the next loop. So we'll apply. Okay, let me use another color, black, I guess. Let us apply KVL to mesh 2. So when we apply KVL to mesh 2, what do we get over here? This is minus, this is plus. So 10 minus 6 I2 minus 10 I2 minus I3 minus 2 I2 is equal to 0. All right. So if we rearrange it, what do we get? We get over here, this will be 6, 10 and 2. That will be minus 18 I2 plus 10 I3 is equal to minus 10. Let's call this equation number 1. All right. So this is the mesh analysis by applying equation number, by applying the KVL to the mesh number 2. Now let's apply the KVL to mesh number 3. So let me minimize it. Okay. So let me use another color, blue in fact. KVL to mesh 3. So KVL to mesh 3 gives us minus 10 I3 minus I2 minus 6 I3. Here it will be plus minus, so it will be minus 12. Then it will be minus 3 I3 and minus 4 I3. That will be equal to 0. All right. So that is the equation we get over here. Let us check. This is on the right hand side. It's already solved. So that's not this thing. So what we will get over here is, let's club it together. So you will have 10 I2, then it will be minus 10, minus 6, minus 3, minus 4. So this will be minus 7, minus 13 and minus 23 I2, and that will be equal to 12. Let's call this equation number 2. All right, and so let's solve this equation number 1 and 2 to find the value of I2 and I3. So let's put it in the matrix form. So here we'll have I2, I3. Here we will have minus 10 and 12. All right. The coefficient of I2 is 18 and 10. Here it will be 10 minus 23. So if you work it out, the value of I2 is coming out to be solve this in simultaneously using your calculator, I2 will come out to be 55 upon 157 amperes, and I3 will come out to be these right hand side document I'm just using for the answers. You'll get it as minus 58 upon 157 amperes. So please cross check these answers. All right. And now what is the value of Norton's current or ISC? Norton's current is I1 minus I2. So let's write that. Norton's current is I1 minus I2. That will be 6 amperes minus I2, which is 55 upon 157 amperes. So this will come out to be, if you work it out in your calculator, this will come out to be 5.65. So 5.65 is my Norton's current. Got it? Now next thing what we will do is we'll draw the Norton's equivalent circuit. So for the third part, we'll draw the Norton's equivalent circuit. Norton's equivalent circuit consists of a current source of value IN in parallel with a resistance Rn, and then we have terminals A and B, and then we connect the load resistor RL. Okay, what are the values of IN? IN value is around 5.65 amperes. Rn value is around 13.65. And what is the value of RL? Let us check it out in the numerical. The value of RL is 5 amperes. So we need to find the current through 5 ohms resistance. So this will be 5 ohms. Now current flowing through 5 ohms can be determined using current division rule. So what is the current division rule says? Other resistance, that will be 13.65 divided by total resistance into the current value. So if you work it out in your calculators, the current value is coming out to be 4.135 amperes. Okay, so that is the value of the current which we get by Norton's theorem. All right. So we'll do one thing. Let's check it out in LTspice. So our theoretical part is completed. Now let us build the circuit in LTspice and check these values. So we will cross check the value of Rn, that is Thevenin's resistance. So let's build this circuit. So let me keep it over here and let me open LTspice. Let me minimize it. All right. So I'll measure our RAB or Rn. So for that I need to connect this network. So let me use all the resistors. I'll rotate it. So this is 1, this is 2, then over here, then we have 1 over here and 2 over here. So these are all the resistors. Let me connect them together quickly. These are all connected. This is open circuit. Okay, one more resistor is required. Let me copy it from here. Connect it over here. All right. So yeah, now the circuit will be complete mostly. Yeah, leave it open because it is open circuited. All right. Let me fit to screen. Okay, so these are my terminals A and B. Let me extend it over here. This is A and this is B. So we need to find the equivalent resistance between A and B. Let me mark the nodes as A over here and B over here. So basically there is no ohm meter or to measure the resistance in LTspice. So first let me write the values over here. This is 6. This will be 3 ohms. This will be 10 ohms. This is 2. This will be 4. This will be 3 ohms. 6 ohm resistance. All right. So to find the value of resistance, we'll connect a voltage source of a known value, and we'll divide the voltage source with the current flowing through that voltage source. All right. So let me give that value as 10 volt. All right. So if I give the value of the voltage source as 10 volt, and let's find the current. Also we need to add the ground. So let me see that the negative of the voltage source is connected to the ground. like this. So let me run the circuit. Remember, in LTspice, current flowing out of the voltage source is considered negative. So I'll press OK, and here is I of V1. Don't consider the negative sign because I've already told you the reason why. It will be 10 divided by 0.732484, and that is coming out to be 13.65. So yeah, 13.65 is the value. Let me note it down over here. So I right click, go to draft, go to comment, and I'll add the current. Okay, I have not added the current over there. Let me simulate again. Let me copy the current. So I'll calculate the value of Rn actually. So this is the revised current. V1 value is around 10 volt, right? Which we have given. So how will you calculate Rn or RAB? That will be V1, that is voltage, divided by current flowing through that voltage source. Okay, that will be 10 divided by 0.732484, and that if you work it out in a calculator, that is coming out to be 13.6522 ohms. So this is the value of Norton's resistance, that is Rn, 13.6522, and we got it as 13.65. All right, let's go to the next part. Now need to calculate the short circuit current. So what I will do is I'll remove this over here. Let me take this circuit only. Okay, I need to do certain adjustments to the circuit. So as follows. So this resistor, I'll push it on this side because I have to add a voltage source over here. All right, so let me add a voltage source. So this is my voltage source. I'll rotate it and add it over here. All right, next I need to add the voltage source over here also. So let me do that. I'll add the current source first, rotate the value and place it over here. First of all, let me remove this and let me push this a little this side because I have to add a voltage source to it. Little bit more this side, and then I'll push this current source over here. Okay, I'm remodifying the circuit so that we can calculate ISC directly. Then we have to add a voltage source over here like this directly. Yeah, so this is A and B. We need to short circuit it, but when we short circuit it, we cannot measure the current. So to measure the current, what we require is, now all the things are done. Okay, these connections are left. So let me make this connection over here. So now mostly the circuit is complete. Let us check it out. This is 6 amperes. Let me give 6 amperes. This will be 10 volt. This value of voltage source will be 12 volt. This is 3 ohm, 4 ohm, 10 ohm. Yeah, as it is. Now what I was saying was, in order to calculate the short circuit current, we need to short circuit A and B. Alright, that is fine. We'll short circuit A and B. But in order to find the current, short circuit current, we need an ammeter. So let's use a 0 volt voltage source as an ammeter. So I'll make the voltage as 0. So 0 volt voltage source, if we add, it won't disturb the circuit, but this will act as an ammeter. So now current flowing through this V3, I of V3 will give me IN directly. So let me simulate and let me click on, okay, I need to add the ground also. So I'll add the ground over here. All right. So this is my ground. Now I need to calculate ISC. Okay. Current flowing through V3. So let us search current flowing through V3. Here it is. Current flowing through V3, that is 5.6469 64968. So 5.65 approximately we are getting the current. So this is 5.64968, and that is the Norton's current which we get. Okay, 5.65. And then by application of, so that is also coming correct. Then by entering the values of I and Rn, we can easily calculate the value of current flowing through 5 ohm resistance. All right. So this is how you can measure short circuit current and Norton's resistance using LTspice. So yeah, that's it for this lecture. Next time we'll start with see one more example of Norton's theorem, and we'll move on to the next theorem. All right. So that's it for today. Thank you all for joining.